Okay, so let's start. Today's topic is information retrieval. I think this topic we were studying under the data models, but by right, this probably is not a data model subject. Somehow, the information retrieval based engines like Solar, Elasticsearch, they are currently being used as NoSQL databases also, and that's the reason why we had to touch upon this subject. What I will cover here is the mathematics behind how these engines really work, and it's going to be a very high-level introduction only. And those who are interested, I think we will have to take it offline and do some deeper studies on this. This is a very interesting subject, by the way. So we will cover these 4 topics. One is the information retrieval problem. I will define a sample problem that we normally face on a daily basis. The idea is to look at how the primitive rudimentary ways are there to solve this problem. And then we will look at one particular example called Boolean retrieval and try to understand what it serves and what are the limitations compared to the real world information retrieval challenges. And we will learn some key terminologies that are used in this space. And the last one is one particular mathematical model called vector space model, which is predominantly used in search engines today. And this is where the crux of the discussion will lie. And once we have a good understanding of this, we will know how these Solar, ELK engines work. To a larger extent, how Google search engine works also. Now, obviously, there are variations and optimizations they all adopt inside, which we wouldn't know. But Solar ELK, to a larger extent, they use an engine called Lucene, which is the text search engine underneath. It's a common engine, and these guys are running some optimizations on top of that. And that's a open source. We can actually look at the Lucene source code and understand how this vector space model is implemented inside it. Now, let's get to the discussion here. Information retrieval problem. So let's look at this particular corpus. By the way, corpus is a terminology they use to represent a repository of documents or a knowledge base is what a corpus is. In this example, Shakespeare's collected works, and this is a collection of all the plays written by Shakespeare, roughly about 1 million words in it, roughly about 32,000 unique words in it. So this particular thing really amazed me. 32,000 unique words is what he used. And if you ask me, I probably use 32 words. Generally, that's how my vocabulary is. Mostly I use 32 words. If you minus off all the was, this, that, all that, that's all it is. So if intelligence has any correlation with the number of words you speak, probably Shakespeare is 1,000 times intelligent than me. That's where it is. Interestingly, we can all look back and see how many unique, distinct words that we are using on a daily basis. Anyway, so let's say the question here is determine which plays of Shakespeare contain the words Brutus and Caesar, but not Calpurnia. So this is an example query that we have. Let's say we have a directory full of this Shakespeare's collected works documents. Right now, what is the most common technique we adopt to execute this kind of searches? Anyone able to say? So let's say we all are on Linux or on our Mac, and we have a directory full of documents. What is the most common tool?
Grep.
Fantastic. Grep is what we use. Yes. So grep obviously would work in this case. 1 million words is not a big deal for a decent laptop that we have. It would work. Now, what are the limitations of grep? Suppose if we have a data of web scale size, billion documents, massive, that cannot even fit into one computer. Obviously, that will fall apart. What if our search is slightly more intelligent? Like I want to search for every sentence that has Romans and countrymen in the same sentence, which are nearer by 5 words each. So that kind of query, grep won't be able to support. The moment you use something like near, grep will take near as another text to search for. It will not understand the syntax of near. Right? So here comes the notion of query language that is important in information retrieval. Most importantly, what about ranked retrievals? So grep wouldn't be able to organize the results in such a way that this is the most relevant document and that's the least relevant document. It doesn't matter to grep. As it goes through the directory in certain order, arbitrary order, whatever it finds is matching, it will keep emitting that. So, but nevertheless, we can from here itself we can understand information retrieval means some kind of relevant document retrieval, some kind of query language that helps us to intelligently retrieve our results. Now, let's look at this Boolean retrieval technology, which is going to solve the problem of, you have a huge amount of documents and grep is going to be slow. And if you can apply a simple mathematics, it's going to help us here. So let's imagine that these are all the documents we have, and these are all the words inside the document. And we create something called, this is called an inverted index. So normally an index is a book and all the words inside the book, right? This is what we call an index. An inverted index is all the words in the corpus and in which book these words are present. So it's very simple. If you come across the term inverted index, that's what this means. So the words Antony, Brutus, Caesar, and if they appear in a document, you put a 1 there. If it does not appear in a document, you put a 0 there. It's pretty straightforward Boolean mechanism. Now this gives you a bitmap of this particular word in this corpus. So our query is Brutus and Caesar, so we construct this bitmap. So take Caesar, it is 110, 111. So we just take that as a bitmap. Not of Calpurnia, as you would have figured out by now, take the negative of that. So this is 0, 1, 1, 1, all the way. It's like this. So to arrive at our result, Brutus and Caesar are not Calpurnia. It's just a matter of finding the intersection. So 1, 1, 1 will give you the intersection is 1. The rest of them is 0, and here is 1, 1, 1. That will give you 1. Now, if you take this result, automatically you will get Antony Cleopatra as the result, and then this one Hamlet as the result. The rest of the documents won't appear. So it's very, very straightforward. Computers can do this very fast. So imagine now you solve the problem in one way, which is you are not really doing character by character match, which is going to be very expensive, and you have simplified it by using mathematics, and you got results retrieved in multiple folds faster. But now, what are the problems in this? If your documents are a million documents, constructing this bitmap is massive, and then to do the bitmap operations is going to be expensive. Nevertheless, it may become expensive. But one important problem it cannot solve is ranking the documents. This cannot do at all because you have reduced it to a binary, whether the term is present or not. Therefore, you have completely lost the capability to rank the documents. So that's a simple analysis of any model that we take. What are the terminologies or what are the measurements a search technology can be used to? How do we rate the search technology? Now we come across all these the measurements for it. So document corpus, we saw what it basically means. The relevance can be described as the results personal to the information needs of the user. So here is a very subjective terminology. It is pretty much says that you read what's in the user's mind and then retrieve the results and order them in that priority. So an example is user may say pipeline leaks, whereas your document may have pipeline rupture. Obviously, this is still relevant to the user, but from a text perspective, it doesn't match. Nevertheless, it is still relevant. So that's what relevance is. It's a very tall order to ask for because natural language is ambiguous on itself. Now, effectiveness of a search engine, again, can be measured by two factors called precision and recall. So it's a term that uses two other terms. Now, if you look at precision itself, how we can define precision is what fraction of the returned results are relevant to the information need. So, for example, if you search by SIFT in the noises repository somewhere. So we have all our pre-sales documents, user guides, and every kind of document we have in our company. If you search by the word SIFT, now if it returns 100 documents, and in those 100 documents, only 10 documents are really, really relevant. So SIFT is referred as an analytical real-time analytical engine, right? Even that document comes out, let's say. So, but only 10 of them are really, really relevant, and the rest of them are not, and therefore your precision is 10%. That's what it basically means. So, of all the return results, how many of them really have read the user's mind and have been relevant? That's what it means. Whereas the recall here means what fraction of relevant documents in the collection that were returned by the system. So let's say the collection itself has 100 documents which are relevant, but our system has only pulled out 10 from them. Now its recall is very, very low in this case. So in this scenario, what could have gone wrong is that during indexing, the indexing was not correct, or the indexing did not take care of the semantics, did not take care of all possible synonyms, etc. And therefore, the return result is very, very low recall. So for a search engine to be more relevant to the user, it has to have very high precision and very high recall also. So that's the way to measure how these engines are really performing. And if you ever write a search engine, this is what is the measurement is going to be to rate it. So far, so good?
Yeah.
Okay. Now, let's look at the ultimate model that is practically implemented in search engines called vector space model. This is going to be a bit of mathematics. It needs a little bit of imagination. And I will leave it at a higher level, and if you are interested later, you can go into the mathematics. It's very interesting. I mean, it's nothing great behind it. It's just vector mathematics. Pretty basic, but it's a very creative application of vector mathematics into document search problem. Somebody who has come out with that, I have to really, take my hats off to this person. This is what we call taking a solution from a completely different domain to solve a problem from a completely different domain, which is absolutely mind-blowing when we look at it. So what this model talks about is the factors are something called a term frequency, which basically means the number of times a term appears in a document. So it's represented by term frequency of a term given in a particular document. So if you take SIFT user manual, take the word SIFT, if it appears 100 times in that document, then the term frequency of the term SIFT in the user manual is 100. That's what this basically means. Yeah, very, very straightforward. Now, there is another terminology called document frequency, which is also very important in the vector space model. Basically, the number of documents in a collection that contains the term T. So let's say if our collection is every document in noises, and then the document frequency of a term, let's say the term is SIFT. Let's say of all these documents, let's say 1,000 documents we have, if 100 documents mention the word SIFT, then the document frequency of the term SIFT is 100. Yeah, so far so good, very, very straightforward. Now the issue here is that when we take some of the words which are very commonly used in the corpus. So for example, if you take this example here, Reuters collection of certain documents, a corpus. This has about 800,000 documents. And if you take all the words and try to find the document frequency of the words, car is mentioned in 18,000 times. Yeah, sorry, in 18,000 documents. Auto is mentioned in 6,000 documents. The term burst is mentioned in 25,000 documents. Now, the problem here is words like this, right? Words like this will have very serious side effects in search. So, for example, if I'm searching for best auto, let's say best auto is what I'm searching for. The term best itself, because it appears in too many documents, in any kind of formula, when this document frequency appears, because this is an outlier, it can completely devalue the rest of the words. You see the logical problem here? So these are outlier kind of words, which may make the scores irrelevant because of their very high frequency in the corpus. So we need to find a way so that we can offset this impact of these bigger words, yeah, or high frequency words. And
Brother,
usually, yeah.
I don't understand what is the problem exactly here.
So okay, the problem is if you write any formula which has the document frequency as one of the components inside it, and because the document frequency are very big for such words, the score, the final score is more skewed by this presence of these words, right? So that is a problem here. So if you take the word the in any document, and if a search is based on search starts with the also, obviously this word the is going to be appearing in a million times compared to the normal word, and this big million times presence of the word will completely squeeze the formula results. Any formula. I'm not talking about any particular formula here, but if it is a component in the formula, the document frequency is a component in the formula, this is an outlier. So we need to find a way of eliminating these outliers. For example, the word the I mentioned, you can remove it from the entire indexes itself because it has no meaning as far as search results are concerned. So you can remove it. But words like this, best, or even words like sift, which is going to be the most common word in all the documents. So such words, we have to find a way of moderating their impact to the search query results. So the technique is called inverse document frequency, and it's very simple. What we do is take n, which is the number of documents. So let's say if it's 800,000 documents, and take the words like best. Obviously, if this is the denominator here, this is a bigger number. Therefore, n divided by that bigger number is going to be a very small number, and you take a log of it to just make it smaller. So it becomes like this. So the inverse document frequency, the document frequency is very high, but inverse document frequency becomes very low for this. Whereas you look at these words like auto, which are appearing in very smaller number of documents. But whenever you search for it, these smaller number of documents, right, obviously must have a bigger weightage at the end of it because this word is rarely appearing in only those documents, and therefore these documents must have very high value in it, and hence the inverse document frequency will be slightly higher for these things. So essentially, if document frequency is very high, we want to keep the inverse document frequency to be the exact opposite of it. Okay. So if this example itself, if you take, if I search for best auto, let us say, because some document best appears many times and auto appears smaller number of times, or even auto appears zero number of times, such a document may come very high because the score alone has become extremely very high, and it skews the results. So such effect can be moderated if we take the inverse document frequency of it, and therefore if the word appears in smaller number of documents, it is going to have a slightly higher impact to select those documents. But if the word is universally present everywhere in every document, it should have lesser impact in selecting such a document with such a word. So that's what it means. It may not be very intuitive at this stage, but bear with me. Let's see some examples and it will become clear. Now, how do we put these two things together? So here is the most intelligent way of finding a weightage of a word in a document. It's called TF-IDF, which is the very commonly used terminology in this domain, TF-IDF weighting. Now, that can be computed as the term frequency multiplied by the inverse document frequency. So if you look at this has all these three desired results built in it. So for example, the most commonly occurring words, right? So in here, the most commonly occurring words has a low IDF here. So if a word is present in all documents, now this is going to have a very low score, and therefore the end result will be the lowest, very low score also. So look at this, lowest when the term occurs virtually in all the documents. So all the words like the, best, a, and are if you take big data documents, the word big data is going to be universally present in every document we have, and therefore that the word big data itself should have very low weightage when it comes to selecting the documents. That's what it basically means. Otherwise, a document can just have big data, big data, big data mentioned in it infinite number of times, and that is all enough to have this document appearing on top, no matter what search you do. Yeah. So that's what this basically does. Or suppose if there are rare words, words appears in a very lesser number of documents, they will have a very high IDF, and therefore the end result is also going to be very, very high. So it says TF-IDF is highest when T occurs many times within a small number of documents. And therefore, those small number of documents, if a search contains exactly those terms, that small number of documents will have higher ranking, um, uh, even though they have these high frequency words in it. So that's the idea. We can take some examples and work it out, and it will be proven that always this is going to be the best way to rank a term in a document, the weightage of that. So now, how do we put this together? How is it going to help us at the end of the day? Is where we have to look at a little bit of vector mathematics here. So if you take any document, forget about the TF-IDF so far. Let's look at from a logical perspective. Any document, let's say this document has money appear in it 6 times. Sorry, this is hidden behind this graph. There are 6 times money mentioned in it. So you can take this document as a vector, and it's a two-dimensional vector because our documents only has two distinct words, either money or laundering. These are the two distinct words. This is imaginary world. So you have a 2 dimensions here, and you have a 2-dimensional vector also. So money is appearing 6 times is basically this vector. The laundering is 0, but money appearing 6 times. So you have this vector here. A document which has money laundering, two times money and 1 times laundering is this orange vector. And another document that only has laundering, just one word and no money in it, this document is this particular green vector, just 1, 0. Now, if I ask you from a human perspective itself, this orange vector, which document is it close to? Obviously, you will say it is close to the blue document because if you look at the angle, this angle is a smaller angle compared to this big angle here. So obviously that's what you will say. You will take this angle differences, right? Obviously, you will not consider the vectors, the magnitude, because magnitude is a wrong measurement. I mean, imagine another document which also has money twice in it. Although these two documents are supposed to be very close to each other because the angle is 0, right? But this magnitude is very, very different here, and therefore you should not take the magnitude at all. You will only take the angle between them. So mathematically, the function that gives a high score when the angle is small is called the cos theta function. This again you can go back to trigonometry and recollect these things. So a cosine of 0, if the angle between the two vectors is 0, the cos theta is going to be very high. If the distance between them is very high, for example, this vector and this green vector, it's 90 degrees. If it is 90 degrees, cos theta will be 0, which is very low value. Therefore, you use something called a cosine similarity or cos theta of the angle between the two vectors as the measurement of how close these two vectors are. And cos theta, obviously, in vector mathematics, it's basically the dot product of two vectors is what is going to give you the cosine similarity formula at the end of the day. Basically, it's cos theta of two vectors, right? Obviously, it has one more component which has the magnitude of two vectors multiplied here, but we can ignore it. The dot product of two vectors is sufficient. So essentially, if we take documents as vectors, and if you look at the cosine similarity between the two vectors, whichever has the cosine similarity to be very high, or the angle is small and the cosine value is very high, those two documents are close to each other. Very, very simple. Illustrated with a two-dimensional vector document with two words in it. This is the same if your document has 1,000 words in it. So all you have to do is to build this vector space model, vectors with 1,000 components in them. I mean, you can't humanly visualize such a space, but mathematics is very straightforward. So it's a vector of 1,000 dimensions, and if you take for each word, word by word, if you construct at the end of the day, if you construct the cosine similarity, you will have two documents. Although they have 1,000 dimensions, you will suddenly have documents which have a very high cosine similarity, and you can say that these documents are close to each other. So you have completely reduced a text search word problem into a mathematics problem, which computers can execute very fast. And this exactly is the reason why search engines can give you such fast results, irrespective of you are searching through millions and millions of documents. End of the day, the mathematics behind is like that. But now we are talking about documents and queries, right? Now it doesn't matter how documents themselves are related. It is not important for us. For us, the query, how close a document is to a particular query, is what we are looking at, which is not difficult. All we have to do is you consider your query also as another vector, because your query is nothing but a phrase that you are searching for. So if you can imagine a document with that phrase, that is basically your query, vector query, and you have other documents which are also vectors by themselves, and you can compute these scores. A score of a query compared to a particular document is nothing but the vector dot product of these two vectors. So basically, we are talking about query dot product of D1 is basically this angle that you will get. Similarly, the query with the rest of the documents, and you choose the document which is going to have the highest similarity, which is in terms of a vector, it's very close to any particular document that will have a very high score. Now, if you sort it, obviously by the highest score, you will definitely get the document that is that are closest matches. So the component of a vector, right, is what is going to be represented by TF-IDF. So if you take any document, let's say the document has words like SIFT big data in it. So SIFT is one dimension. You compute the TF-IDF of that. Big is one dimension. Data is another dimension. So you compute three TF-IDFs, and you will have a three-dimensional space, and therefore you can perform this mathematics. Since you constructed your dimensions using this formula, you have already removed the effect of these frequently occurring words, that skewing effect you have already eliminated also, and therefore you have a very fast retrieval system. So this apparently is what is happening behind Lucene. Now again, I kept it at a very basic level. Obviously, this itself is, if a document is huge, like millions of words in it, you are now going to have millions of computations in each document, and you are going to have so many other documents. Therefore, there are many other optimizations that were invented to keep things even faster. But I'm not going into that part of mathematics now. So this is the basic. Now, how do we relate it to our problems? So you can take a JSON document, right? A difference between an unstructured document, like a web page, and JSON is that you have some amount of structure in JSON. You have the keys and the values. Now, nevertheless, you index the keys and the values, and you are eventually constructing the TF-IDF scores of each of the values in it. And the search engine now is a little more informed, because in your query, you can also mention the key and the value that you are looking for. Therefore, it's going to narrow down the amount of search terms only to those particular keys. Otherwise, what is happening behind is still the vector space computation, and it is behaving like any other normal text search engine only, except that the results are going to be very more accurate, because now you are using the exact terms. I hope I have introduced this at a very high level. Obviously, in a session like this, we may not be able to understand and appreciate the entire implications of this. This is a subject where we have to sit alone and try to think about it, try to recollect a little bit of mathematics, and then suddenly the dots will clear. But my objective is purely to introduce the model and for you to start your own journey into this. That's what I wanted to cover today. Any questions?
Raja, as compared to normal text, what I'm not able to understand is how this JSON documents can be indexed in a better way, because still the key and value both are there, okay, but both are the words for the engine. Both has to be indexed, and both similar vector product we need to calculate for both of the words, right? But after calculating the what is that TF, the scoring.
Yeah.
So how does it matter that if it is a key value pair or it is just a text document?
Well, for the engine, it doesn't matter. But when you retrieve the results, what happens? Suppose if the word appears in two different keys, let's say, but in your search query, if you are able to specify that this is the key in which I am looking for a particular value, therefore the results are less ambiguous, right? So that's what it is. I mean, if you take a document is what they call the bag of words. It does not matter in which order the words are arranged. Suppose lazy fox and fox lazy will return you the same document as a result.
Yes.
But, yeah, that's a little bit of ambiguity that you're going to avoid. Just because your document itself is structured, your query can make use of it to eliminate a little bit of ambiguity.
But ideally, performance would be the same, right?
Ideally, it'll be the same behind. Yeah, what happens behind is the same. Okay. Any other question? Okay. If not, we can stop here. Like I was saying, if you're interested in this in the subject, you may have to sit with it by yourself. There is a textbook called Information Retrieval Handbook. This is where I took this material from. This is the book, and it has, it's pretty old actually, but it has every information expressed in a very academic manner. So it's pretty deep. I can share this. This is I hope this is licensed. So yeah, that's where I got all the material from. So you can follow this book also. It's 2008. Okay. All right. Let's stop here then.